so I will not be talking about outflows, but I will be continuing this trend that we've started of moving further and further away from the galaxy by studying the CGM around ISO-8, which is the galaxy that Braun studied for her first paper. So just to make sure everyone's on the same page, the CGM is generally defined as the interface between the interstellar medium and the intergalactic medium, and the boundaries here are quite fuzzy, although the interstellar medium boundary, we think we've found that. This gas is generally found to be bound to the galaxy out to about the virial radius. And the CGM contains a large fraction of baryons, so it seems to contain at least 50% of baryons in galaxies, where the CGM mass is much larger than the ISM mass. And the CGM is important for galaxy evolution studies because it contains a record of all of the past gas flows. So the accretion that comes in from the IGM, the outflows that are ejected from galaxies, and the tidal streams that are stripped from galaxies all must pass through and are hosted by the CGM. So this is ISO-8. It's a nearby starbursting galaxy. It was the pilot galaxy for the Duvet survey. I'm not going to focus much on the gas within the disk. That was the Duvet project, but I'm going to go beyond the disk and out into the CGM. So we know that ISO-8 is a really good target for studying the CGM in emission, which until recently has been very difficult to do. But it's great because it seems to have this active baryon cycle. So we know it's starbursting. It has a star formation rate of 10 solar masses per year. And Braun has found outflows across the entire disk, as we've already heard. But it also has a low metallicity with a value that's about 5 times lower than is typical of its mass. So both of these points suggest that ISO-8 must be actively accreting a significant amount of material that is low metallicity, so it's diluting the ISM metallicity of this galaxy, and it is fueling the starburst. And in fact, we know from VLA data that there's a considerable amount of H1 gas spanning the distance between ISO-8 and a nearby companion that's much smaller, that's about 60 kiloparsecs away. So about 70% of the H1 gas mass in this system is actually contained within this H1 plume, which, whoops, wrong button, which is this area right here. So we were motivated to observe, to look for the CGM in emission with KCWI because we had already this central Duvet pointing in the blue box right here, where we had only spent 20 minutes exposure here, but we saw emission everywhere in the ionized gas, so the O3, O2, and H beta. But we spent 2 hours each on 4 other exposures with KCWI. 3 of them are on this H1 plume, so we were looking to see if we could see accreting material in this ionized gas. And then we also have a 4th pointing off of the H1 plume as more of a control field to see if the gas that we happened to observe on this plume was only associated with the plume or was more of a CGM component. So here is the O3 surface brightness map with KCWI, where the signal to noise ratio is greater than 7 in every location that we see here. But we found emission from the CGM everywhere we looked. We found it all the way out to 30 kiloparsecs, and it likely goes out much further beyond. So that was actually quite exciting. But we can start to look at things like the surface brightness profile. So how does this gas change as it moves away from the galaxy? So this plot shows the surface brightness of O3 as a function of distance from the galaxy, all the way out to 30 kiloparsecs. The different point colors, so the blues show you the gas that is more associated with the galaxy itself, so the disk, going out to about a couple times the 90% radius of optical light, so that's the R90 value here. The purple points are the emission on the H1 plume, and then the cyan points show the gas that is off of the H1 plume. So a couple things to notice here are that as you move outwards from the galaxy, the surface brightness decreases, but also that there doesn't seem to be much azimuthal variation. So the gas on the H1 plume and off the H1 plume seem to have similar surface brightnesses. I'll get into that in just a moment. But there seems to be an interesting shape to the surface brightness profile here. So we went in and we fit it with two different equations. So the blue points we fit with an exponential, as is typical for disk galaxies. So this has a scale radius of about 0.5 kiloparsec. And then the CGM pointings, the purple and cyan points, are well fitted by a power law with a slope of about -2. So what seems to be interesting here is that we seem to have found the transition between the ISM and the CGM in this galaxy, which up until now, no one had been able to see, and it's always been a really fuzzy boundary. What's also interesting is we see similar behaviors in the other two emission lines that we measured. So here is the O2 doublet. The exponential has the same scale radius as the O3, but the power law in the CGM is a little bit steeper. And we see a similar behavior in the H beta as well. Again, the similar scale radius in the disk, but then the CGM power law is actually a little bit more shallow than the O3 emission. And this r to the -2, roughly, power law is actually similar to what was found when Zheng et al. Stacked SDSS galaxies and looked for H alpha emission. And they found this power law held all the way out to a megaparsec. So, but that was for stacked galaxies. This is for an individual galaxy. So we expect this power law to hold in this galaxy as well. Another thing to note is that I've also plotted the H1 column density, just roughly scaling it with the ionized gas. And it seems to remain elevated out to 30 kiloparsecs, whereas the ionized gas decreases. So these two line tracers seem to be tracing different components of the CGM, whereas the H1 seems to be accreting onto the galaxy and fueling that starburst. The ionized gas seems to be more of a diffuse CGM component. All right, so we have an idea of where the gas is located, but what are the physical conditions of this gas? So we can look at the ionization of this gas using the O3-2 ratio. So here we have the O3-2 ratio on the y-axis as a function of distance from the galaxy. And what we notice in the ISM, so the blue points, is that as you move outwards from the galaxy, the ionization decreases with radius, and that's because we are we're being photoionized by fewer and fewer H2 regions as we move outwards from the galaxy. But then beyond about a radius of about 4 or 5 kiloparsecs, that trend reverses and the ionization goes back up as you're in the CGM. So what is happening here? Well, we can compare the O3-2 ratio to the R2-3 ratio, so this gives you an idea of ionization on the y-axis and metallicity on the x-axis, and try and see if this gas is photoionized by H2 regions. So here we can see that the IRSO-8 disk, which is the yellow star, is consistent with SDSS galaxies, so it's a typical galaxy in the local universe. But the CGM points, the circles, are not consistent with the photoionization from H2 regions. So it does not line up with the photoionization tracks from Keeley and Dopadov. So the CGM is doing something different. Another thing it could be doing is being shocked. So it could be that mechanical energy from turbulence or energy deposition from outflows is shocking this gas. So it could be interacting with the ISM or the starbursting outflows in this disk. And it seems to be the case. So here we have a different set of line ratios that give you an idea of shocks in the gas. And so again, the IRSO-8 disk is consistent with the SDSS galaxies on this O3 to H beta versus O2 to O3 plot. But the CGM points, the circles, again, sit off of the galaxies, and they are more consistent with shock models. It's also possible that the extragalactic UV background starts taking over the further and further away from the galaxy you are, so the galaxy becomes less important in ionizing the gas. All right, so in my last minute, I just wanted to ask a question. How much ionized gas mass have we measured? Because the baryon budget of galaxies from quasar absorption lines has suggested that the CGM should make up over 50% of the baryons in galaxies. So we can make quite a few assumptions that some of these have quite a lot of uncertainty, but we measure a total CGM mass between 4.4 kiloparsecs, which was that boundary between the ISM and the CGM, all the way out to the virial radius, which is the rough boundary of the CGM. We get a total mass of 10 to the 10.5 solar masses, which is comparable to what we've measured with quasar absorption lines. But how does this compare to the other components of the galaxy? Well, the stellar mass of the galaxy was 10 to the 10 solar masses, and the H1 in the disk is 10 to the 9 solar masses. So what we're finding is this cool CGM has a mass comparable to the stars and the ISM of ISO 8, but there's still a lot of uncertainty in this measurement, so take it with a grain of caution. I'll leave you with my summary slide and ask the question, is there always this clear ISM-CGM transition? We don't know. We need more observations. And we also need to constrain the electron density in order to get a better mass estimate. Thanks.